Hello and welcome. Today we are pulling back the curtain on artificial intelligence to look at its most fundamental building block. We're talking about the single, tiny engine that powers, well, pretty much everything.
It's a question that sounds like it's straight out of a sci-fi movie, right? How on earth can a machine actually learn or make a decision? Well, you might be surprised to find out that the answer isn't some huge, complicated secret. It actually starts incredibly small.
And that's really the whole idea right there. To build a thinking machine, scientists looked for inspiration in the best thinking machine we know of, the human brain. They decided to build a digital version of our most basic component, a neuron. This one idea, this one brain cell, is the foundation for everything else.
So let's get right into it. What is this thing really? What is an artificial neuron?
Okay, so you can think of it like a tiny little data processor. It does three simple things. It takes in information, it does a little bit of math to figure out what that information means, and then it sends a signal on to the next neuron in the chain. It's this huge chain of communication that lets an AI and our own brains make sense of a world.
All right, to really get how it works, we need to pop the hood and look at the parts inside. Every single artificial neuron, no matter how complex the AI, is built from the same 5 basic pieces.
So, you've got your inputs, which is just the raw data coming in. Then you have weights, which are super important. They tell the neuron what data to pay attention to. The bias gives the result a little nudge one way or another. The activation function is the final boss. It makes the big decision. And finally, you get the output, the message it sends out. Now let's zoom in on a couple of the coolest parts, the bias and the activation function.
So what is this bias? It's a pretty clever trick, actually. It's just a fixed number that gets added to the total every single time. Its whole job is to make the neuron a little more flexible, kind of like giving it a starting advantage or a handicap to help it make better decisions.
And this is the perfect way to think about it. Those 5 extra marks aren't part of the student's actual score, right? They're an adjustment, a little bit of help added to the total to make sure the outcome is fair. That's exactly what a bias does for a neuron. It's a little helper.
Okay, so after all the inputs are weighed, and that bias is added in, the neuron has one final number, but now it has to make a choice. Does it fire, or does it stay quiet? This is the moment of truth, and that's where the activation function comes in. It's the gatekeeper. It looks at the final number and decides yes or no.
And what's really cool is that these activation functions have different personalities. A threshold function is totally black and white. You're either above the line or you're not. It's a simple pass or fail. A sigmoid function is a little more subtle. It gives you a probability, like saying there's an 85% chance this picture is a cat. And then you have ones like ReLU, that stands for rectified linear unit, which only pay attention to strong positive signals and just ignore all the weak background noise. Different jobs require different kinds of decision makers.
All right, we've seen all the individual parts, so now let's assemble them and actually watch a neuron think. We're going to use a really simple example, figuring out a student's final grade.
The process is basically a 5-step recipe. First, you get your inputs, in this case, the student's grades. Then, you multiply each grade by its weight, which is how important that subject is. You add all those up, toss in that helpful bias, and then, for the grand finale, you run the total through the activation function to get your final answer.
Okay, let's plug in the numbers. Let's say our student got an 8 in science, a 7 in math, and a 6 in computer. Now, we've decided that science is the most important subject for this calculation, so we give it a higher weight of 0.4. And just for good measure, we'll add a bias of +1 at the very end. So let's build our equation. You take the science grade, 8, times its weight, 0.4, plus the math grade, 7, times its weight, 0.3, plus the computer grade, 6, times its weight, 0.3, and then you tack on that +1 bias right at the end.
When you do that first round of multiplication, you get 3.2 for science, 2.1 for math, and 1.8 for computer. Now, all that's left to do is add everything up. And that gives us a grand total of 8.1. But hold on, what does 8.1 actually mean? Right now, it's just a number. It doesn't become a thought until our neuron makes a decision about it.
And this is where our activation function kicks in. We've set a very simple rule for it. If the final number is greater than 5, then the output should be excellent.
Well, since 8.1 is definitely bigger than 5, the neuron fires off its signal. And just like that, it has completed its thought process. The final result? Excellent. See? Simple, logical, and really powerful.
Now that you've seen how it's done, you get the basic mechanics. So I think it's time to put you in the driver's seat. Let's have you run a calculation.
Okay, it's your turn. So grab a piece of paper or just open up the calculator on your phone. We're going to use the exact same setup as before, just with a different student's grades. You ready?
Here are the new grades: a 5 in science, a 6 in math, and a 7 in computer. Remember, the weights and the bias are exactly the same. Go ahead and run the numbers. I'll give you a second. Okay, did you get 6.9? Since 6.9 is also greater than 5, the neuron's decision is, once again, excellent!
Believe it or not, what you just did, that simple little calculation, is the fundamental operation of all artificial intelligence. So now let's zoom out. We've just been playing with one neuron, but modern AI isn't built from one. It's built from millions, sometimes billions.
And this right here is probably the most important thing to understand. An AI isn't just programmed to be smart. It learns. It starts out by making guesses, and with every calculation, it slightly adjusts its weights and biases, getting a little bit better, a little more accurate through trial and error. It learns by doing, just like us.
So I'll leave you with this final thought. If one tiny neuron, just following a few simple rules, can figure out if a student is doing well, what happens when you connect billions of them together? All of them learning, adapting, and communicating with each other at the speed of light. Well, that is the incredible power and the true magic of artificial intelligence.